Hello, and thank you for joining us today. My name is Graham Howe, and I'm a Topside Business Development Manager here at OEG, and I'll be your host as we introduce you to OEG's Metocean services. A few housekeeping notes before we begin. We'll be sharing the slide deck upon request. Please use the chat if you would like a copy. We will answer questions at the end, and please use the Q&A for any questions. We'll also be monitoring the chat if you raise them there. For those of you not familiar with OEG, we are a global energy solutions business working across the full range of energy sectors. I'm just going to pause for a moment because my slide has not rolled on.
It is not rolling.
One moment. We seem to have a situation where the slides aren't rolling forward. I can continue to talk while that's being repaired. In 2025, the group was acquired by Apollo Capital for $1 billion, supporting our aim to become a worldwide leader in the energy services market. Our renewables arm is comprised of 14 market-leading businesses acquired over the last 5 years to create a single service provider for the sector. As can be seen from this slide, we've worked on over 90% of the world's offshore wind farms, supporting all of the market's developers. We work across the full project lifecycle and continue to add new services in order to create a strong product offering for our clients. As with other service offerings, Metocean services are the latest in this range of solutions. We've combined the group's strengths with market-leading personnel to create a service to meet the project's requirements across its full life cycle. I'd now like to introduce Chris Comyn, our Head of Offshore Technology. Chris is a Metocean scientist by profession, and he's worked with all of the leading names in the sector. His past employers will be familiar to anyone who has worked in the global offshore wind sector in the last 20 years. Chris's extensive experience makes him uniquely suited to speak on the topic of Metocean data and the offshore wind sector. So, without further ado, I will hand over to you, Chris.
Thank you very much, Graham. Welcome, everyone. Thank you for joining us today on our first in what will be a series of webinars. Metocean is a broad topic, so I want to make it clear that I'll be focusing on operational oceanography rather than delving into the detail of the data. My career has been mostly operational, from diving in the National Marine Aquarium to deploying the first Metocean buoys on Dogger Bank back in 2010. I've worked all over the world on multiple deep water projects from the high Arctic to the Southern Atlantic. And today I'm surrounded by a great team of highly skilled technical specialists pushing the sector forward. It's a real pleasure to be able to share some of that experience with you all today. There are two groups here today, Metocean specialists and everyone else. This webinar is geared towards everyone else. So to begin with, I'll set out what I'm talking about. Metocean is two words, meteorology and oceanography. We are focusing specifically on the physical processes, so we're not going into the biology or the chemistry. The wind profile, which is speed and direction up from sea level to about 300 meters above, and we're looking at the change in that profile. So as what you call wind shear takes place, where the change in the speed and the direction from the bottom to the top. The same can be said about the current profile, with instruments either looking up through the water column or down through the water column. Again, looking at the changes through that profile in speed and direction. The waves, there are numerous parameters, and like I said, I'm not going to delve into the data, but waves in particular affect all aspects of what we do in the marine environment. Water quality, which is conductivity, temperature, the pH, dissolved oxygen, suspended sediment concentrations, all again having an impact on what we do, whether it's vessel-based or structures that we're building in the environment. Water level, which everybody will know as the tide. We refer to that in terms of mean sea level, so it's the 0 point either above or below mean sea level, or the lowest astronomical tide. So the heights above the lowest point you will see in the astronomical tide. The tide itself is made up of two components: the astronomical component, which is the sun and the moon predominantly, and then the meteorological forcing as well. Now, we achieve all this through any array of sensor and system integration. I'll go into all of that in some detail in the coming slides. which will give us either your engineering data or data as a service. Again, I'll talk about that in some detail. You'll see on these slides here, I don't know if you can see my cursor, maybe on this one here, there is a circle around this instrument here, which is a type of ADCP, which is an acoustic current Doppler profiler. So it uses sound to measure the profile up through the water column. And this device down here, which is a floating LiDAR buoy, based on similar principles, uses lasers to measure the atmosphere above the instrument. Now, I've circled them because they are relevant to a couple of slides later on, so just bear that in mind. This instrument here sits on the seabed looking up, and this instrument here sits on the sea surface, also looking up. So why do we bother? Because meteorology and oceanography will shape every phase of your project. In the early phase, you've got the site characterization, where you need to understand the nature of the environment. What are we dealing with here? The wind resource assessment will determine your final investment decision, which essentially gives you the go-ahead to proceed with any development, well, for offshore wind, sorry. The waves, the currents, and the physical characteristics I touched on in the previous slide, they will all have a physical impact on your structures. You can see this image here is AI generated, but it demonstrates quite nicely what I'm trying to get to. If you've got large waves and the structures that you've designed and installed can't cope with the physical conditions, i.e. the waves will hit your platform, you will experience significant damage. So in the early stages, we characterize the environment we're going to be building in to make sure that if you've got a platform like this, then it is sufficiently high off the sea surface so that these waves wouldn't impact on it and create that damage, which history has taught us can be quite significant. So how much steel do you need to withstand, say, 30 years of operational life, and also things like mobile sediments? I've said about suspended sediments and the sort of the seabed that you'll be mounting your structures on, and how you set out your cable arrays, and whether or not you need to have protections in place like rock dumps. All of that will be informed by Metocean data. Moving through the phases of development into operations, construction, and O&M, you're always going to have vessel movements. Now, vessels are extremely costly, and what you want to do is reduce the sail and fail. So if you've got heavy lifting operations or the movement of personnel, what you can't do is take your vessels out to find out that it's above operational limits. Within a day or two, the data will be paid for if you've got a large construction vessel just on standby on site. Now, when you consider floating offshore wind farms, all of these things I'm talking about will be multiplied. And it's not always clear to the end user what it is that they're looking at. It's important to ensure that the Metocean data is accurate and detailed for the Metocean specialists and the design engineers, but it's also clear to the non-experts. So, for example, a vessel master will know what you're talking about with significant wave height, but that can be described in terms of HS or HMO or H1/3, all of which approximate to the same thing, but it can be confusing if you don't know. So how hard can it be? Well, there is an awful lot of limiting factors in what we're doing. You've got third-party interference. Typically, you'll have collisions. It's accidental, and it happens way more than you'd expect. But sadly, we also have sabotage. Certain fishing communities will see our activities as a threat to their livelihood, and there have been incidents in my past where we've discovered that instruments have been deliberately sabotaged. The nature of the environment, extremely energetic. That's exactly why we're there, and there are extreme events throughout the year which can be incredibly damaging. This image here was on Dogger Bank when I mentioned that I did the first of the Metocean deployments out there back in 2010. It was just after I deployed the first buoy. We had a significant storm event that saw waves recorded above 12 meters, which I assure you is not fun to be in when you're on a boat. The other physical processes like corrosion, where you get electrochemical degradation of some of the equipment that we put into the water. You may have heard that stainless steel doesn't corrode. I assure you it does. This here is probably been in somewhat of an anoxic environment, and then you have this serious pitting and corroding on the shackle here. And we're lucky that that one didn't fail. All of these things need to be considered, whether or not you're actually designing the structures for the actual development, or it's the surveys and the measurement campaigns that we would be doing. You can see in this image here, the mobile sediments had an impact on the data here. So this is neap tide going to spring back to neap here, and there was a passage of a sand wave in that time. This data here would have been completely unusable, unsalvageable. Now, I pointed out those instruments earlier, the ADCP and the floating LiDAR buoy. You'll see on this one, the biofouling has been quite significant. Now, these instruments would sit on the seabed for maybe 3 months, and you limit the deployment periods really for data security, because you can have these sort of colonizations, if you like, of these dog whelks, which will just sit over the top of your instrument. They've got a lovely hard substrate to lay their eggs upon, and unfortunately is a complete loss of data. So within a month, that device was colonized, and we lost 2 months worth of data. This one here, this was during an extreme event where the floating LiDAR buoy that I pointed out on one of the earlier slides, unfortunately, was flipped upside down by an unusual coincidence of very large and very steep waves. But as I said, that instrument is supposed to be looking up through the atmosphere to measure the wind profile. There was a significant loss of data in that incident too. And there are things that we can do to prevent this. You can put out notice to mariners. So the Kingfisher Bulletin will issue updates to mariners on the type of the deployment, the polite requests to avoid the instruments that we have. But it's not always the case. The fishing fleets will continue to fish. And the mooring design process itself, and there are reasonably sophisticated methods now of modeling moorings and simulating moorings and ensuring that you've got the correct level of design, because you can't over-engineer it. It will suppress the ability of the instrument to function. Some of the smaller wave buoys, they need that free movement. So you could over-engineer it, and in doing so, you'll have poor quality data. But if you under-engineer it, well, it'll probably break free from its mooring. So all of these things need to be considered, not failing to acknowledge that it's dangerous by its very nature. I've not focused on safety because it's a webinar series all into its own, but it's important to acknowledge that when working in a dynamic environment with complex tasks, things can go wrong if you don't have strict controls in place. So this was an incident that was published in the IMCA Safety Flash back in 2024, where there was some lifting operations going on in a large buoy. The buoy was being controlled with a tagline, but the tagline got snagged. The crane continued to slew, and that created a tilt in the lift. The tagline then parted, and the buoy swung and hit someone on deck. Thankfully, that person they weren't seriously injured, but it did go down as a high potential near miss. And it was found that they were stood within the line of fire. They didn't have adequate controls in place. People weren't deemed competent. And we have things like the G+ life-saving rules, which we all say that we live by and we implement. But in reality, when you're on deck, it is easy to become task focused. And what we need to make sure is that these controls are sort of baked into the culture. It is a part of what we do collectively. All of it's not just a process and a document that exists in the office. It's what we take offshore with us. So the impact of all this is to develop an effective campaign, which I think is important to have a two-way relationship between the developers and the suppliers, to understand at each stage what it is that we need to be delivering. What are the data outputs? Who are we talking to and why? Is it wind resource assessment for the FID? Are we talking to the Metocean experts to determine the design criteria, so the front-end engineering design? Is it during operations, and are we providing site-specific weather forecasts, which goes into the planning, the marine coordination, the operations and maintenance teams who need to have efficient and safe operations, and then throughout the life of any structure as well, to make sure that things are being monitored and well understood, which will inform the planned and preventative maintenance throughout its life. It's worth and important saying that you will not get 100% data. This doesn't happen because of the things I've spoken of: third-party interference, it's an extreme environment, corrosion, fatigue, biofouling, all of these things that I've covered in the previous slide. Data is everything. That is the reason we're there. That is the reason that we put all of this effort and resource into making sure that you have the highest quality and data continuity, which is basically what we would be able to bring with that combination of communication, sensor and system integration, and the Metocean expertise that we're discussing here. So I'm going to go into a little bit of detail now on the various systems that you'd need to have in place to achieve the outcomes from the different phases. Now, early on, with site characterization, you're in blue water, there is nothing there, so you have to have more systems. It's usually at the early stages of a wind farm development. Like I said, with Dogger Bank, that was back in 2010, and they're still in the construction phase now out there on what is now the Sophia site, the Dogger Banks A, B, and C, and Dogger Bank South. So that's 16 years in the making, plus the time that it took to go through consent. So with the moored systems, I touched on mooring design and modeling, incredibly important to make sure that you're getting the best out of the sensors, understanding the size and the complexity of the site that we're monitoring to make sure that you get the correct mooring spread, and then getting the data back to shore. Data security is incredibly important. Like I said, if you don't have the full data set, you're not going to have a full understanding of your site. Got a quick case study here, which looks at an active site that we've currently got on the Inch Cape wind farm. What I've not said is that we're also quite often dealing with aids to navigation. They're often lumped in together because although they're not data buoys, they are marking buoys, but they have to have the same considerations for mooring design and the type of buoy for meeting the requirements of an aid to navigation. And we've got a number of buoys marking the Inch Cape site, two of which are Metocean buoys delivering waves and currents to the control room, which you can see down here. That's our control room in Edinburgh, receiving the live data from site. Moving through the development phases, once you've actually got structures in place, you can go from moored data to fixed data, and that's an area of particular interest for me, because I think that if you can move seamlessly through each phase of the project, where you've got that continuity of data, you've got the same quality, then all of the end users will be getting the most out of any Metocean measurement campaign or data service. Now, with the fixed systems, like I said, as soon as you've got a structure in place, it's beneficial to put these fixed systems in place. You'll have lower OPEX cost. They can be hardwired, although they can also be self-contained if it's in the very early stages, and you're likely to get a higher data return because it's less risk of third-party interference. This approach brings a much more consistent stream of data. Case study for you here, it's fixed but on floating, because this is a floating offshore wind farm off the coast of Portugal, which brought some additional considerations, because obviously the floating structures, they move, and this is a fixed measuring device, so it has to be heave compensated, and because you're interested in the coming direction of the waves, there has to be a correction for direction as well, So we had a GPS compass integrated into the system. You can see here that there's a pole mount with a weather sensor as well. And again, all of that data is sent ashore and used daily with the site control rooms. This is what it will look like. So the data that goes ashore is part of an in-house developed software package, and that can be integrated into your system, so it can live within your network. So it'll be secure according to your own cybersecurity standards, or it can be standalone. We do maintain ISO 27001, and we have the necessary processes to comply with the IEC 62443 standards if required. Now, all the data is gathered by the suite of sensors, integrated, and then sent to the data services cloud by the most cost-effective means. So it could be through a Starlink connection. It could be integrated into your hardware that you've got out there. And it's also worth saying as well that we can integrate legacy sensors. So if there's anything that you've got on your assets that you would wish to see into the online data dashboard, all of that is possible. And then with a final case study, this is an operational wind farm that we have 3 sensors out in the southern North Sea, directional wave riders, all securely integrated into their SCADA network, which again is also displayed in real time in the customer control room. Now, I've gone through this very quickly. It has been a whistle-stop tour, and there's an awful lot more to consider. I do hope it's been educational, and if you'd like to know more, please don't hesitate to get in touch. Thank you very much for taking time out of your day, and I will now hand back to Graham.
Thank you very much, Chris. To summarise, OEG are the only organisation in the market today that offers a range of services across the full project lifecycle, including both moored and fixed assets. Our team have, in particular, over 20 years' experience in the field of moored Metocean data systems and the deployment of offshore fixed sensing solutions. Our client services include market-leading sensor suites combined with expert design, deployment, and maintenance. There we go. Always the last word that gets you. We hope that we've enjoyed our presentation, and now I'd like to open the floor to any questions, please. So, Chris, the first question that we have coming up is, are there ways of guaranteeing data return from moored systems?
Certainly not guaranteeing, no. Greater levels of confidence, yes. I mean, technology is always stepping forward, and we're having more and more confidence, I suppose, in the systems like Starlink, for example, which has got much better coverage, still reasonably costly, and things like data harvesting now, where you can have autonomous vehicles, they can be sent out and they can harvest data off the seabed, for example. Like, you know, the seabed frame that I said got covered in all of that, those dog whelks. It could be that you have a autonomous vehicle goes out, and if they've both got acoustic modems, then they can communicate, and then you can determine whether or not that it's still on site, and then you can also download the data. So you've got guarantee data return by those methods. But on moored systems, it is very difficult. There are so many limiting factors that all you can really do is manage down those risks rather than completely eliminate them.
Thank you very much. The next one is obviously from a very evil person who would like to know which is more accurate, the fixed or the floating wave measuring solution.
Well, I mean, they are different. They ultimately measure the same thing, and they are calibrated in such a way that means that you are getting the same data. The means of measuring is different. Obviously, the buoys themselves are surface following, so they have they're measuring their heave and their own displacement on the water surface, whereas the wave radars are measuring the air gap. So it's fixed, and the radar measures the air gap between the sensor and the sea surface. So the means by which they're measuring is very different. And of course they are calibrated, and they are both very accurate, and they will record approximately the same thing. But because of the nature of the measurement rates, the sample rates, you won't always get exactly the same data. There will always be slight variations in the output that you get from the instrument. You don't get instantaneous measurements. You get a period that is sampled, and then that sample period is averaged and broken down into its component parts. So whilst I'm giving you a bit of a rambling answer, it is quite a complicated thing to measure. As you look out, you see that waves are made up of waves upon waves upon waves from different directions. So unless you've got two instruments that are actually side by side measuring exactly the same thing, you will get slightly different measurements. They're both very accurate. They're both very reliable means of measuring waves. But at the different phases of a development where you don't have any structures, you have no choice but to use a buoy. As soon as you've got a structure in place, it makes perfect sense to put a fixed system in place. So I can't really give you a solid answer. They are both very good. It just depends on the stage of the development.
That will feed into the next question, but I've got a little note here that one of the audience has raised a hand, so I'm not particularly sure how I'm supposed to respond to somebody raising their hand. Hopefully our team will give us an answer. We've got 3 more questions to go, Chris. The one that you just said, which is the move from the moored system to the fixed system, really does trigger the next question, which is what is the cost difference between a fixed and floating system? So we clearly have a procurement person on the line.
Well, it also depends exactly what it is you want and how many you want of them and for how long you want it. It does vary on device type and complexity too. So a simple wave buoy, you're looking at tens of thousands. The same with a wave radar system, tens of thousands. You start to add in more complex, like you can have a single sensor for the wave radar or a 3-way, which will give you the direction. So then you're starting to build up the complexity of the system. Same with the wave buoys. You might have a simple wave buoy, you might have waves and currents, you might want waves and currents and met. I tried to get that across really in the presentation. It depends very much on what it is you want, why you want it, and who is the end user. Of course, you're always trying to work towards getting the most cost-effective solution, and it's not really easy to give you a straight answer.
If I can, as a BD person, if I try and put my spin on this one, what I'd be looking at is really the difference on a fixed platform is you probably get payback against the cost of a floating platform over 3 to 4 years. However, the risk on the floating platform of a mooring failing or a vessel running over it is considerably higher. So it makes sense in a kind of OPEX version for the fixed to be the chosen solution, because you can amortize it over time in a way which you wouldn't be able to do with the floating system with a higher risk.
Which is exactly why you should, in my opinion, move from floating to fixed as soon as you have that opportunity to do so.
Right, I've got to be a little bit careful here, Chris. I'm mindful of time, and we've got at least 4 questions to go. So the next one's a cunning one. On a sustainability note, what factors have you considered regarding the use of advanced mooring systems to minimize seabed damage? And I'm going to use the word benthic scour here because it's always a favorite, that one.
It's always been an interesting one for me because over the years, things have changed, certainly going from oil and gas into renewables, because it wasn't seen as a problem to discard some of the anchors on the seabed. You'd have sacrificial anchors, and we would often use old anchor chain, which is fairly inert. And to some degree, people would argue that you are actually creating nice little environments for the wee beasties to live upon. As we came into the offshore wind world, that was not acceptable, and we had to remove everything from the seabed. For a while, we did look at degradable concrete. It was called biodegradable, but it wasn't. It was chemodegradable concrete. But the process that you make the concrete and the plasticizers within the concrete was environmentally damaging. So I was never a fan of that anyway, certainly not over the inert steel. Now it is just a matter of making sure that you've got an adequately designed mooring with sufficient lifting capabilities, I suppose, to be able to lift these anchors out of the seabed, so that you don't part your lines. When we're in control, that is. Occasionally, it's out of your control. When large vessels strike the buoys and they drag them, they fail, and then occasionally you do have lost anchors on the seabed. But that's typically the worst of it. Of course, you can get ropes and chains that go with it, but basically the answer to the question is it is designed in the early stages to make sure that you've got a means of recovery to be able to pull the anchors off the seabed without parting a line.
So I'm getting a flag that we're getting close to the end of the webinar. I'm going to try and keep running till somebody pulls the plug on us, because we've got some good questions. If you don't mind, Chris, do you mind if I answer the next one?
It's fine by me. Yeah.
So you mentioned forecasting. Is this something you provide, or do you pull this in from a third party? I'm just going to finish this question, then I am being told to wrap up. Do the operations planners go on forecast or real-time data at the location? Typically, most projects will go for a minimum of 2 forecasts, and they will mandate them. And that will be a requirement where they will work on it. However, what we can do is we typically feed our Metocean data into the forecast as well, in order to provide a comparable data set and improve the accuracy of the forecasts. If you want to say anything else, Chris, and then unfortunately we've got to stop.
No, just nodding along. Yeah, that's good answer.
Okay, guys, we've got a couple of questions, Steve and Anne, both really good questions. We're sorry we ran out of time. We will follow up with answers to you. Thank you very much for attending the event with us. And if you'd like to learn any more, please feel free to contact us, and we'll be happy to answer any questions you may have. Thank you very much indeed for your time.